Cheers, everybody. It is a real pleasure for me to be here. Dear ministers, senators, colleagues and friends, I've been here once before, and I'm very delighted to have been re-invited and be here with you again, and to talk to you about livestock and climate. This is a topic that I live and breathe. I've been in Davis now at the University of California in Davis for 20 years, and I'm an air quality specialist. So I study the impacts of livestock on air quality and climate. Not just finding how much livestock contributes to the air, but also how to mitigate, how to reduce impacts of livestock on the environment. And so I was asked to share with you slides for about an hour and then have a question about the presentation. So as was mentioned during my introduction, on the one side, I'm a professor and I teach and do research, but I also am the director of the CLEAR Center at UC Davis, and I was asked to talk briefly about what that is. The CLEAR Center is a center, a sustainability center that does two things: research on sustainability and communication. And in the past, communication, in my opinion, was drastically undervalued in a way where an increasingly more often interested public, particularly young public, asks questions about where their food comes from, and they don't get factual information. And so I thought we need to change this, and I established the CLEAR Center. The CLEAR Center has two cores. The one is in research. We do a lot of research trials on quantifying greenhouse gases, quantifying other pollutants from beef, from dairy, from swine, and other operations. We do this either on campus, or we do it also on commercial farms and ranches, oftentimes in collaboration with our state and federal agencies, such as the California Air Resources Board, the Environmental Protection Agency, and so on. The reason why that's important to me is because for research to be accepted, to become policy, we need to have the buy-in by the agencies that regulate it. So we oftentimes do that. We do research on methane, and I will share some of that with you today, methane and other greenhouse gases, quantifying those impacts of animal agriculture and mitigating those. We do research on mitigation, as I just pointed out, meaning how do we reduce greenhouse gases? For example, the methane that's belched out by cattle or sheep or goats, how can we reduce it through feed additives? What can we do with animal manure to reduce emissions from that sector? The focus is really on quantifying how much comes from the livestock sector and how can we further reduce. And today I will talk to you particularly about one major issue, which is methane. You just saw on some of the previous slides that methane is a big deal for Uruguay. Greenhouse gases are a big deal from agriculture in Uruguay because it's such an important sector for your country. In my opinion, it's paramount for you to get the quantification of greenhouse gases and the impact of these greenhouse gases on warming correctly. Because this sector is as important to you as the automobile sector is for Germany. In addition to research, we do communications. And here we have really started to get involved in a major way with all different kinds of newspaper and TV appearances. A lot of research has been done and communicated via social media. I started a Twitter career 2 years ago. I never would have thought that I would ever use Twitter, because as a scientist, you don't want to use something like Twitter. But now that I am using Twitter, I'm very happy that I do, because I reach people who I've never reached before. High school students, college students, journalists, policymakers, millions of people. In 1 year alone, 20 million people. That's how many people you reach with a platform like this. And without social media, I would have never been able to reach that many people. And that many people who really matter. These are the people who I try to reach when a teenager asks, where does my food come from and how is it raised? When a college student wants to know, is it true that livestock emits greenhouse gases and how much? When a policymaker says, is this really such a big deal? What can we do to reduce it? Then these people need to find answers that are based in science and not in propaganda. We do have a lot of facilities at UC Davis that I built, multi-million dollars. Unfortunately, they are very expensive, but we have invested significant amounts of money in order to quantify emissions from livestock. Both, let's say, enteric emissions, meaning what animals belch out, what comes from manure, not just greenhouse gases, but all kinds of emissions. The center, the CLEAR Center that I'm directing, is supported by a number of international, national organizations, as well as industry. All of those have various contributions to make to our center. And then we also collaborate with NGOs, not in a financial way. They're not financially contributing, but they are also working with us in order to get their narrative included. So it is very important for us to be inclusive. So I will now shift. Just really briefly wanted to mention the CLEAR Center to you. I will now shift to livestock and climate. So everybody is aware of the Paris Climate Accord. And you are aware, I assume, of the fact that the Paris Climate Accord really has a temperature goal of not adding additional 1.5 to 2 degrees centigrade to our climate. That's the temperature goal. So we don't want this additional warming to happen. And so when I, during my talk, mention additional warming, then that's the reason why. The Paris Climate Accord does not have an emissions goal, it has a temperature goal. The Paris Climate Accord doesn't tell you you have to reduce so and so many tons of carbon. It tells you don't add additional warming. The question for us in the room today is, how can we prevent the livestock sector from adding additional warming? Because that's what it's all about. Greenhouse gases matter for one reason and one reason only: warming. So I will skip that really quickly. I just wanted to mention, when you look at our media, nationally and internationally, you see all different kinds of newspaper titles that are very negative around livestock and climate. Okay? And that's not just true for the United States, that's true globally. I don't know to what extent it's happening here, but through my observations, a lot of this is not based on science. It's not based on facts. It's based on getting clicks and, in many cases, fear-mongering. And the time is right to infuse some science into this discussion and communicate that science in a way that people understand. We have to have a fact-based discussion around livestock and climate, and that is important in no other country more than here, because livestock is so critical to your economy. So first of all, globally, and this is really just a global statistics here. Globally, when you look at all greenhouse gases and which sector contributes to these greenhouse gases, then globally, this is pretty much where we stand. Energy, it's called here, that's the use of fossil fuel, oil, coal, and gas, and the related industries such as transportation, power production, and others emit approximately 3/4 of all greenhouse gases. Globally, agriculture and forestry combined around 18%. You see their livestock is parceled out in dark green on top. According to this statistics, globally, livestock and manure is 5.8, but other things are included when it comes to livestock as well. So currently, the number the FAO uses for global livestock is 14%, 1/4. But that global number is grossly different compared to national inventories, okay? So the US number is very different from the Uruguayan, from the Paraguayan, from the Ethiopian, and so on. There are vast differences in percent contribution of livestock to national greenhouse gas inventories. I think what is out of the question is that livestock is a significant contributor to greenhouse gases. You see here on top that about, let me see if I can use this here, that approximately 7 to 8 gigatons of greenhouse gases stem from the livestock sector. And you can see here, of all livestock-related greenhouse gases, the actual feed production makes up 40% of the total livestock carbon footprint, feed. And then the rest is livestock itself. And when you tease it out, beef is the number one. That's the number one greenhouse gas contributor within the livestock sector, followed by dairy, and then you have small ruminants, buffalo, pigs or pork, and poultry. So these are FAO numbers, and I think these numbers are pretty reliable now. We have, over the last few years, quantified what the impact of livestock and poultry is globally and in many national inventories. We have done that. That research has been published and peer-reviewed and published. It's in the literature now, so we know where we stand. 10 years ago, when I was here the last time, we didn't know that. Today, we do know that. And we also have a much better idea today how we can further reduce these emissions. And that's critical. I will give you a little 101 on greenhouse gases and why we care about greenhouse gases. Most people in the room will know, but just to make sure we are all on the same page. What this slide here shows is the sun radiating down solar beams to the surface of the Earth, and with it, solar heat. Normally, that solar radiation would be reflected back into space if there weren't these so-called greenhouse gases. Gases such as CO2, methane, nitrous oxide, and others. And these greenhouse gases form a blanket over our atmosphere, retaining some of the solar heat in our atmosphere and preventing it from escaping into space. So greenhouse gases forming this blanket are actually very important for life on Earth. Without greenhouse gases, it would be way too cold on Earth. So we need this blanket of greenhouse gases. But the problem now is that human activity produces too many greenhouse gases, and that means the blanket is getting too thick. And too much heat from the sun is retained in our atmosphere, and that generates global warming. So CO2, methane, nitrous oxide are greenhouse gases that we are concerned with. We don't want to produce too many of those. So the greenhouse gases that we are generally concerned with are three: CO2, methane, and nitrous oxide. And when these gases are compared, and this is now very important, when these gases are compared to one another, a so-called matrix is used called global warming potential, GWP 100. This GWP 100 compares a gas like methane to CO2. It compares a gas like nitrous oxide to CO2. And it converts them using this factor, 28 for methane and 265 for nitrous oxide. So in other words, if you have a dairy or a beef operation and you produce 10 tons of methane, then all you have to do is multiply the 10 times the 10 tons of methane times 28, and that's 280 tons of CO2e, CO2 equivalent, CO2e. So this convention of GWP 100 has been used since 1990, so for the last 30 years, and it is used all over the world up until today. Recently, some criticism has occurred around the use of GWP 100, and I will share with you what this criticism is and why this criticism matters to you. So remember, GWP 100 is the unit used to convert methane and nitrous oxide to CO2 equivalent units. So if you just look at this slide, it would appear as if methane was simply a stronger version of CO2, a much stronger version of CO2. And it is true, methane traps the heat from the sun 28 times better per molecule than CO2. So it's powerful. But that's not the only difference between these gases. This slide here is a very important one. It shows the global methane budget. On the left side of this slide, you see various sources of methane, including fossil fuel production, agriculture and waste, biomass burning, wetlands, and other natural emissions, totaling 558 teragrams of methane per year. All sources in the world combined amount to 560 teragrams globally annually. What is left out of this discussion is the fact that methane is not just produced, and this is really important now, methane is not just produced, but methane is also destroyed. And you see this on the right side. There are sinks of methane amounting to a total of 550 teragrams. In other words, globally 560 teragrams are produced and 550 teragrams are destroyed. And the net, the difference between the two, is 10 teragrams, a number we further seek to reduce, but that certainly is very different from just looking at the one side of this budget. Remember, methane is different from other greenhouse gases. Other greenhouse gases are not destroyed. CO2 is not destroyed. Nitrous oxide is not destroyed, but methane is destroyed. But currently, that destruction is not accounted for as it should using GWP 100. This is really important, okay? Really important. There is an atmospheric removal of methane. And if you look at this slide, you see a large arrow pointing down. Underneath it says, sink from chemical reactions in the atmosphere. What does that mean? That means that if my fist were a methane molecule, this methane molecule would, within about 1 decade, about 10 to 12 years, meet another molecule in the air called a hydroxyl radical. And this hydroxyl radical destroys the methane molecule. It destroys it. It takes about 1 decade for that to happen. And it has always happened. This is not new to any chemist or physicist in the world, but it is relatively new in the public policy domain. And to me, this is critically important information to be infused in any discussion around methane and how it warms the planet. And you will see in a minute why. Methane is not just produced, methane is also naturally destroyed. That's called atmospheric removal. And that leads to a very significant difference between methane and other greenhouse gases. That difference is how long this gas stays in the atmosphere and warms the planet. You see here that CO2 that we burn, when we burn gasoline with our cars, CO2 is put out through our tailpipes. That CO2 stays in the air for 1,000 years. CO2 has a lifespan of 1,000 years. Nitrous oxide is also a long-lived climate pollutant with a lifespan of over 100 years. But methane, because it's not just produced but also destroyed, has a lifespan of a little over 10 years, 10 to 12 years. You will now ask, well, why does that matter? It matters profoundly because methane does not accumulate in the atmosphere. It's both produced and destroyed. But the other greenhouse gases do accumulate in the atmosphere. And you will see in a minute why that really matters. But before I go there, I want to talk to you about where the carbon that makes it into methane, where that carbon comes from and where it's going. Particularly on, let's say, the livestock side. Methane chemically is CH4. Where does the C, the carbon in the CH4, where does that C come from? It all starts with photosynthesis, the process by which plants, like grasses, take sunlight, water, and a form of carbon to make cellulose or starch. So plants, in order to do photosynthesis, need carbon, and they pull the carbon from the atmosphere. They pull the carbon from the atmosphere in the form of CO2. So it is the CO2 carbon that makes it into plants. The plants make carbohydrates from it, whether that's starch or cellulose, but the plants make carbohydrates from that carbon, that atmospheric carbon. Then a cow comes along and eats the plant material, and with it the carbohydrates. And in her rumen, she produces methane gas. Microbes produce methane gas. Some of that methane is belched out, enteric fermentation, enteric emissions it's called. And some more comes from the animal manure. But ladies and gentlemen, Is this carbon in the methane? Is this C in the CH4 new and additional carbon added to the atmosphere? Is this C in this methane new and additional carbon added to the atmosphere? And the answer is no, it's not. It's recycled carbon that was in the atmosphere before, but in a different form. It was in the atmosphere before in the form of CO2. It's not new and additional carbon added to the atmosphere. After about 1 decade, this atmospheric removal process occurs it's called hydroxyl oxidation. That's when these radicals, these hydroxyl radicals, kill the methane. That happens within about 1 decade. Converting the methane back into CO2 where it came from. Converting the methane back to CO2 where it came from. So the CO2 resulting from this conversion is not new additional CO2, it was CO2 at its beginning. If you have a constant source, and this is now critically important, if you have a constant source of methane, let's say a constant cattle herd or a constant sheep herd, then these animals produce methane, but at an equal rate for a constant herd, at an equal rate methane is destroyed. If you have a constant herd, the amount of methane produced and the amount of methane destroyed are almost in balance. Almost in balance. A constant herd does not add new additional, and I underline that, new additional warming. A constant herd of livestock does not add new additional warming in general. If you increase a cattle or a sheep herd, that will cause new additional methane, new additional warming. If you reduce methane, and that's very important, if you reduce methane, then you are pulling carbon from the atmosphere. If you reduce methane, you are reducing warming. And that is really important. I don't want anybody in this room to walk out of this room saying, Mitloehner does not think methane is important. Yes, I do. I call methane the fast and furious greenhouse gas. Furious because it's powerful, but fast because it's short-lived. And this works in our favor. You will see this in a minute. On the livestock side, the carbon cycle is cyclical and it's short-lived. Okay? The carbon goes from atmospheric CO2 to plant carbohydrates to methane belched out or coming from the manure, and then again to CO2. But we do not add new additional warming from a constant cattle herd, from a constant sheep herd. How is this biogenic carbon cycle, as we call it, how is that similar or different from other greenhouse gases caused, for example, from fossil fuel? Well, here's the answer to that. Fossil fuels, oil, coal, and gas, are the main culprits globally for greenhouse gases. And what are fossil fuels? Fossil fuels are plants and animals that died and decayed and fossilized millions of years ago. Humans drilled it and fracked it and so on. Therefore, we extracted it from the ground, and then we burned that fossil fuel. And so, as you can see on the left side here, we put that carbon into the atmosphere. But it was in the ground for hundreds of millions of years. That carbon on the fossil fuel side was in the ground for hundreds of millions of years, and over the last 70 years, 70, over the last 70 years, we extracted half of all that fossil carbon. And what, ladies and gentlemen, did we do with that fossil carbon? What did we do with it? We burned it. So where is all that carbon now? It's in the atmosphere. And every time the sun hits those molecules, they heat up, trap the heat, and that leads to increasing amounts of CO2 globally. That we are taking vast amounts of carbon that were in the ground, we are burning them, we are putting them in the atmosphere. And that, ladies and gentlemen, is new and additional carbon. New and additional carbon, causing new and additional warming. Now I go back to the livestock side and how that's different, because the fossil carbon is a one-way street from the ground up in the air. On the livestock side, to the right, you see it all starts with CO2. During photosynthesis, plants take on the CO2 and convert it into cellulose. Some of the carbon stays above ground, but the majority of the carbon goes below ground, into the roots, And then via soil microbes, it is stored in the ground, a process called soil carbon sequestration. Grasslands and forests can pull a lot of carbon from the air and store it in the ground, where it stays unless you plow the land. If you disrupt the land, the carbon will come back out. If you don't plow the land, the carbon will stay in the ground. Soil carbon sequestration stores approximately 1/3 of all human-caused carbon. Soil carbon sequestration stores approximately 1/3 of all human-caused carbon. It is one of the most important ways of locking away carbon, and agriculture and forestry are the only two sectors in society that can do that. Now, of course, our livestock eat the above-ground vegetation, and when doing so, they also put some manure down. By the way, the manure accelerates soil carbon sequestration because it accelerates microbial growth in the soil. Okay? And then, but an unintended consequence of our livestock being able to eat this grass is that they produce methane. But that methane, as I told you, stays in the air for 10 years and goes back into CO2. So what I'm showing here is that on the fossil fuel-related carbon side, we have a one-way street of emissions from the ground up into the air. And on the livestock side, we have a continuous cycle which takes about a decade of carbon going around and around and around. This is not the same. This is different. Here we have new additional carbon. Here we have recycled carbon. Does that difference make sense to everybody? Because of this, because of the fact that methane is not just produced but also destroyed, you see it here, because of the fact that methane is not just produced but also destroyed, and because of the fact that GWP 100 does not account for that, colleagues of mine from Oxford University said GWP 100 does not correctly account for the impact of methane on warming. Even though it's used all over the world up until now, it is not correctly accounting for the impact of this gas on warming. They proposed an alternative unit called GWP star, which does account not just for the production, but also for the destruction of methane. And GWP star, the Oxford unit, also describes the impact of methane on actual warming, not just on CO2 equivalent emissions, but on actual warming. So first of all, who came up with this? GWP star was first developed by a gentleman from Oxford University called Professor Miles Allen. Professor Miles Allen is the IPCC, the Intergovernmental Panel for Climate Change, senior author that came up with the Paris Climate Accord 1.5 to 2 degree goal. He was the one. So Miles Allen is not someone, Miles Allen is the one in the field of climate. He does not understand livestock, I believe. He's a physicist, but he understands greenhouse gases like few others. And he said the way we are counting for methane currently is not right. GWP 100 is not fit for purpose to describe the impact of this gas on warming. He developed this GWP star, and GWP star has been a game changer in my opinion. So first of all, what Miles Allen and others said was that this old unit, GWP 100, that the world has been using, including Uruguay, overestimates the impact of methane from a constant source by a factor of 4. So, for example, here in Uruguay, you have a constant cattle herd. You have had a constant cattle herd for the last 20, 30 years, a constant methane. A constant cattle herd means constant methane source. If you now use GWP 100 for this constant methane source, then that contribution of the constant methane source is overblown by a factor of 4. Miles Allen and his team have said it for years. I have said it for years. But what's really a game changer is that the IPCC last August released their Ar6 report. And in that Ar6 report by the IPCC, they said the same thing. that the unit that has been used for the last 30 years overblows the impact of methane on warming by a factor of 4. The IPCC says it. So the question now is, where does that lead us? Right? Because the world is using this old unit. Now the IPCC says it's not really doing the job accurately of quantifying constant sources, so what shall we do? I recommend that we do use this old unit, but not alone. I also recommend to use the new unit simultaneously, GWP star. Why? Because this new unit will actually tell you what your source of methane, your beef, your dairy, your sheep herd, what they do to climate. GWP star does look at the impact of a methane source on warming. And it does take into consideration not just the production, but also the destruction of methane. GWP star has now found its way into the most recent Ipcc Ar6 report. It's now in there. It can now be used. And I want to show you this here. I know nobody can read this, but this is from the Ipcc Ar6 report that came out last August. And it says, and I quote, emissions, so by expressing methane emissions as CO2 equivalent emissions using GWP 100, overestimates the effect of constant methane emissions on global surface temperature by a factor of 3 to 4. This is not the opinion of one scientist from UC Davis telling you something. This is a consensus report by the IPCC on GWP 100, okay? This same report also mentions numerous times the use of GWP star. You will find it all over the document. Here it is mentioned. It's mentioned throughout the report. So I'm not telling you, forget GWP 100, because the world is using it. But I'm cautioning you that it does not describe the impact of a sector on warming. And I recommend to you the simultaneous use, not just of GWP 100, but also GWP star. I presented something similar to what I'm presenting to you now to the FAO in Rome, the Food and Agriculture Organization of the United Nations. And the steering committee of the so-called LEAP partnership took this to heart and said, we might make a mistake on methane. We might have to revisit some of our policies. So we should install a task force to investigate the biogenic methane impacts, the way we can mitigate and so on. I was part of this task force. 65 members, a very large scientific body, worked on methane for the last year, and the report is about to come out in a month or two. I think this will be a very important report for you, because methane is your Achilles heel in Uruguay, because it's such an important greenhouse gas, and agriculture is such an important source of emissions in this country. So I want to show you how methane is different from CO2, and then also how this old unit GWP 100 compares to the new unit GWP star. So let's imagine that you were to live 20 kilometers away from work. In the morning, you drive 20 kilometers. When you drive, let's say on day 1 here, that's Monday, when you drive, you burn gas, you put CO2 into the atmosphere. On Tuesday, you drive the same distance again, and you now put new and additional CO2 into the atmosphere, in addition to the existing stock from the previous day. On Wednesday, you drive again, and again, you put new additional CO2 into the atmosphere. Every time you burn fossil fuels, you add new and additional carbon to the atmosphere, and that causes new and additional warming. New and additional warming. Currently, methane is treated by most policymakers as if it were to accumulate just like CO2, as if every day that our cattle belch, that were new methane, additional methane. But is it? The answer is no, it's not, because methane is not just produced, it's also destroyed. Methane is not like CO2, a stock gas that accumulates, but methane is what's called a flow gas. It's both produced and destroyed. By the way, you find the the references of these pieces of work at the bottom. So this is from Miles Allen at Oxford. So CO2 accumulates in the atmosphere, but methane does not accumulate in the atmosphere. Methane is produced and destroyed. How does that matter? That matters because of the following. I will walk you through 3 different scenarios. The first scenario is one where methane over 30 years increases. Let's say in a given country you were to increase cattle herds, then you were to increase methane. The second one is where methane is held pretty stable, slightly reduced over 30 years. And the third one is a scenario where over 30 years we strongly reduce methane by 35%. How would these 3 scenarios be depicted using GWP 100, the old unit? GWP 100 would predict that an increasing methane, a stable methane, and a decreasing methane would each add a significant amount of new additional CO2 equivalent emissions to our atmosphere. GWP 100 does not account for the atmospheric removal of this gas, as this shows very clearly. Now comes the new unit, GWP star, and how that's different. GWP star would predict that only if you increase methane, you indeed add a lot of additional warming. That's the blue north of the x-axis. If you add a lot of methane to the atmosphere, you add a lot of additional warming. And we certainly don't want that. GWP star and GWP 100 only agree in the top scenario. If you slightly reduce methane over 30 years, then you don't see any blue north of the x-axis, meaning no additional warming. If you have a stable herd or slightly reduced emissions over time, then you don't add any additional warming, as this slide shows right here. And if you strongly reduce methane, which I promote, if you strongly reduce methane, look what happens here. Now you have a lot of blue south of the x-axis and a negative sign in front of the number. What does that mean? That means that if you reduce methane, you are inducing negative warming. Negative warming is a fancy word for cooling. If you reduce methane, you're pulling carbon from the atmosphere. You're pulling carbon from the atmosphere, you're reducing warming. And that, ladies and gentlemen, is a great opportunity for agriculture. Because what this means is that if we manage to reduce methane, then we can be part of a climate solution. We can pull carbon from the atmosphere as if we were to plant trees which do the same. Reducing methane is a very powerful tool, a short-term tool, to reduce our impact on climate. But with GWP 100, you would never know that, because this unit is not fit for purpose to describe that. GWP star will tell you that. It will tell you that a reduction of methane is a reduction of warming. So now, what does the livestock sector look like globally? These are greenhouse gas emissions from 1960 until very recent, and you see globally livestock greenhouse gas emissions are going up. And that's mainly because many developing countries now have enough disposable income to afford some animal source protein. Many poor countries, oftentimes nutrient deprived, when lifted out of poverty, will be in a situation where the first thing a mother does is, when they have a little bit money left, is to buy an egg, or to buy some milk, or buy some meat. And these countries, many of the developing countries, satisfy this increasing demand for animal source food by growing livestock herds. The Ipcc says that of all livestock emissions globally, 70 to 80% occur in developing countries. So the vast majority. And the reason for this is increasing demand and no efficiencies. The efficiencies in many developing countries are very low, very low. Animals live forever. They are not producing a lot of product. Livestock herds are vast in size. And that's why we see this development globally. But in many countries like yours, the situation is different. Here, you don't have increasing emissions, but most likely either stable or decreasing emissions. In the United States, we have the following situation. We used to have about 140 million beef cattle back in 1970. Today we have much fewer, 90 million, but with this much smaller herd today, we are producing the same amount of beef. 50 million fewer beef cattle produce the same amount of beef. In the United States, we produce about 20% of global beef, while only having 6% of global beef cattle. Okay, so this efficiency is a big deal. So here you see that over time, on the x-axis, we had a decreased amount of slaughter, beef slaughter, but an increasing amount of beef produced in the United States. So a pretty drastic development of fewer animals producing more product. What I'm not at all saying is that we should not be aggressive around methane. I think we should be. In fact, if we are aggressive on the beef side and on the dairy side in the United States, we have calculated that if we reduce beef and dairy by 18 to 32%, then we reach a point by which the beef and dairy sector cross the x-axis, meaning they become climate neutral. These sectors will no longer add additional warming to our planet by the year 2040 or so if we reduce methane by 18 to 32%. That is the point we call climate neutrality. So we will reach that climate neutrality through mitigation of methane. It's not just business as usual. We have to do something differently. We have to become more efficient. We have to use certain techniques, technologies to achieve this climate neutrality. In California, for example, where I live, we have very aggressive goals and laws. One that mandates a 40% methane reduction, 40, to be achieved by the year 2030. At first, our farmers thought this would never be possible. But it is possible, ladies and gentlemen, when and if and when the public sector works hand in hand with farmers. In California, the policymakers decided to not enforce the 40% reduction of methane with rules and regulations and fines, but, I call that the cane approach, but use the carrot approach of financially incentivizing methane reductions. The state of California helps financially the farmers to reduce methane. And the farmers and the state work together. They share the cost. And they reduce methane in a major way, as you will see in a minute. Here's one example. You see an average California dairy. Our dairies are much larger than dairies in the rest of the world. A dairy with 2,000 milking cows is not unusual. It's pretty average. So here you see one of these dairies, and what used to be an open lagoon where the manure is stored is now covered. These covered lagoons are also referred to as anaerobic digesters. They are now covered, and the gases that are generated by the manure are now trapped under the top. It's called biogas, and 60% of this biogas is methane. And methane is flammable. It has a lot of energy in it. So what do these farmers do with this biogas? They don't just burn it and make power like they would have done in the past, but they're taking the biogas and they're converting it into transportation fuel for semi-trucks, for buses. And we now had over 100 dairies doing this, large dairies doing this, putting in these covered lagoon digesters, trapping all the biogas, and making this dairy biogas into transportation fuel. This, ladies and gentlemen, is considered by the state of California as the most carbon negative fuel type there is, meaning the most different from fossil fuels, or the best fuel type there is. And as a result, the state of California pays so-called low carbon fuel standard credits. Low carbon fuel standard credits. And these credits are so high that our dairy industry is flocking to put this technology in. They are now capturing those gases and they are utilizing this. They no longer view methane as a problem. They now view methane as an opportunity. And I view it as such as well. Methane is only a problem if you don't deal with it. Then methane is a problem. If you do deal with it, it can be a major opportunity, even a financial opportunity. Our dairy producers now make half the amount of money that they make for selling their milk by doing this. So it's a significant income source. But what's needed for this to happen is a market. You have to have a carbon market. In California, we have that. The other states are now copying California, and I think other countries will do the same thing. And my hope is that Uruguay will go the same route, because only if you put a price ticket to emissions, people will do something about it. The cane approach does not work. It certainly doesn't work well. I wouldn't say it doesn't work, but it doesn't work well. Make farmers part of your solution, because you need farmers. The world needs your farmers. Enable those people to do what's right. That's my call out to you. Now, you might wonder, how effective has this been, this thing here? This started 3 years ago. 3 years ago. And 3% of all public funds in California to reduce methane, 3% went into the dairy sector to do this. 3%. But this relatively small investment has led to a 30% of California's methane reduction. So there's a 10x on investment for this technology. So our state thinks this is wonderful, and why haven't we done this sooner? But now there's a strong push. I believe in 2 or 3 years, half of our cows in California, we are the #1 dairy state in the country, will have done this. In addition to this, there are other technologies like feed additives, improved carbon sequestration, and so on. We will, ladies and gentlemen, achieve our 40% methane reduction, as the law says, no problem. And our farmers will like it. This is what it looks like. When dairy biogas is converted into renewable natural gas, that's the transportation fuel, this dairy biogas is now going into these semi-trucks, replacing diesel. These semi-trucks no longer use diesel. They now use this renewable natural gas, which burns cleaner. And by doing this pathway, you now reduce the emissions on the dairy, and you reduce the emissions from the transportation fleet. That is the reason why the state is so bullish about this technology, because you have a double whammy. You reduce emissions on the farm and in transportation, and you make farmers part of a climate solution. In addition to this, at UC Davis, we do a lot of research on reducing enteric emissions. That's the belching that animals do. And here we use many different feed additives. Some of them are listed here. We have found that 5 additives so far have been effective to reducing enteric methane by anywhere between 10 to 50%. Many of these additives are absolutely cost neutral or generate higher performance of cows and cattle and sheep and goats. Why? Because 10% of what you feed, the energy that you feed to ruminant animals, 10% of that is lost as methane. It's a net loss to production. You can just as well burn your money by allow cattle and everybody else to just belch normal amounts. It's in the best interest for farmers to reduce methane, because methane is a net loss of production. It is to allow your cow to just belch and the manure to off-gas methane is the same as in the middle of winter leaving your doors and windows open and all of your heat go out. Makes no sense. Makes no sense. So, what does mitigation of greenhouse gases and other environmental pollutants include? How do we get there? How do we minimize environmental emissions of livestock? We have to improve and increase reproductive efficiencies. We have to improve the health of animals through vaccination and treatment. We have to improve the genetics of plants that animals eat, as well as animals themselves, and feed more energy-dense diets. And these 4 factors will allow us to shrink the number of animals we need to produce a given amount of product. This has been effective all over the world and is heavily promoted now all throughout the world. You have done a lot of that here in Uruguay, but there's still some way to go, for example, on reproduction, on pasture management, and so on. I will now walk you through something I call the 2050 challenge. And I spend a few minutes on this. What you see on this slide here, and I show you this, by the way, because Uruguay is such an export nation, okay? What happens in the rest of the world profoundly matters to Uruguay. What you see on this slide are the years 1750 to 2050, hence the name 2050 Challenge. And on the z-axis, you see the total human population on our planet in billions. I'm a little over 50 years old. When I was a little boy, we were right here at 3 billion people. Today, we are here at 7.8 billion people. And by the time I'm an old man, we'll be here at 9.5 billion people. In other words, ladies and gentlemen, throughout my lifetime, human population on our planet will have tripled. We will have 3 times more people on our planet during our lifetimes. But we don't have 3 times more resources to feed these people. We don't have 3 times more land, 3 times more water, 3 times more fertilizer, and so on. And what does that mean? That means that we have to make the very best use of our natural resources, the very best use. And I believe that you're doing that here in this very country. We have to make the very best use of our natural resources, and we have to become as efficient as we know of. You see here on this slide two colors. The one is orange, and that's human population in developed countries, which is plateauing, and human population in developing and emerging countries. Ladies and gentlemen, the reason why this curve is going up is not because every family now has 5 or 10 babies. The curve is going up because of increasing life expectancy, because people live longer lives also in many developing countries. We all want to live longer lives, but as a result, human population is going up. We have to respond to that. We can't just say we don't care. So, while this is happening, this is one of my favorite slides here. It shows the world from space and a circle over Southeast Asia. This circle contains more people in it than the rest of the world combined. More people live inside the circle than outside the circle. And that's not news to you, because this circle is one of your main export markets. And it will continue to be that way. Throughout the world, human population increases at different rates. You see here Southeast Asia increasing by over 40%, but the number one, the hotspot in the world is Africa, with respect to human population increase. So we have a drastic increase of human population by the year 2050. The Americas are relatively stable, and Europe will slightly shrink in human population. While we have a tripling of human population on our planet, the natural resources will not be tripled. What you see on this slide here is, in color, all the land in the world that's arable. Land where you can grow crops for people and crops for animals. But now comes something that I hope you'll remember, because I think it's very visual. Imagine this sheet of paper here, a regular sheet of paper, being the entire size of the world. This is what you see on this slide. The entire Earth is this paper. Now I will fold this sheet of paper, and I will fold it twice. And what you see now is the total amount of land of the world that is actually land. The rest is water and ice. This is how much land we have in the world. The rest is water and ice. This, ladies and gentlemen, is my business card. And the equivalent amount of my business card is all agricultural land in the world. So this here is all land, and this is all agricultural land. This is how little agricultural land we have to feed everybody in the world. Now I will fold my business card into a piece that's 2/3, and the other piece is 1/3. And then I rip my own business card into two. The 2/3 piece of my business card is the agricultural land in the world. That's called marginal land. Marginal because you cannot grow crops there. It's too rocky or too hilly or too dry, or it's not fertile enough. 2/3 of all agricultural land in the world is marginal land that you cannot use to grow crops. So what do we do right now with this land, ladies and gentlemen? What do we do with this land? We graze it. We graze it with ruminant livestock. Why? Because ruminants are the only animals that can digest what grows there, grass. Cellulose in grass. Cellulose is the #1 biomass in the world, the most abundant biomass in the world. And ruminant livestock are the only one who can digest that that biomass and convert it into high-value animal source foods. Without ruminant livestock, ladies and gentlemen, we could not make use of 2/3 of all agricultural land in the world, the marginal land. The same, by the way, is true for Uruguay. The vast majority of your agricultural land is marginal land, and it's used by ruminant livestock. Why? Because it's the best use of that land. Going back to global, the 1/3 of my business card, that is the tiny amount of land that's called arable land. Here we can grow crops to grow food for people and livestock. That's how limited we are. This is how and why it's so important that we make the best use we know of all land that is currently used for agriculture, because if we don't make the best use, we will not have enough feed and we will not have enough food. I don't need to tell you what's happening in Europe right now. The war in Ukraine has a major impact on wheat, a major impact on other grains, a major impact on fertilizers, and all of a sudden the world wakes up and says, is it possible that we will have famines in the world again? The answer is yes, that's absolutely possible. It's actually likely that we will not produce enough food in the years to come unless we make the best use of our natural resources and become as efficient as we can be. Just think about it. About 1/3 of all fertilizers in the world comes from that region of Ukraine, Russia, Belarus. 30%. Same amount of grains feeding the world comes from that region. So it is very important that countries like yours make the best use of your natural resources. This is a slide I like. It is a dairy slide, so many of you are not into dairy, but it's an important one. It shows on the x-axis the amount of milk produced per cow per year, and on the y-axis it shows the carbon footprint of milk production per cow per year. And what you see here are many diamonds. Each diamond is one country and its dairy carbon footprint. So you see there are many countries where dairy cows produce very little milk, maybe 500 kilos per cow per year. In the United States, it's about 11 tons per cow per year. There are countries that have 500 kilos per cow per year. In other words, these countries here on the left need 20 times the number of cows to produce the same amount of milk as one cow in California. 20 times. Production efficiencies and emission intensities are inversely related. When production efficiency goes up, emission intensity goes down. This is a concept many people don't understand. They do understand when it comes to their car. They do understand that a more fuel-efficient car burns less gas to get from one place to another, and burning less gas means fewer emissions. Guess what? The same is true for livestock. A more efficient cow is a cow that produces less emissions per unit of product. It's a very important concept that people don't understand but should, because we need efficient livestock. In countries like India, where we have by far the most cattle in the world, in California we have 9 million dairy cows. In the United States we have 9 million dairy cows. In India there are 300 million. But these 300 million produce very little milk, and people don't even eat the meat. I have another few slides, another 2 or so. There are people in a place like California where I live who say, in addition to changing agriculture, they think we should change it in a major way. They say we need to change what we eat. We should, as a nation, go vegan or vegetarian in order to save the planet from climate change. So I just want to show you a couple slides that summarize what research has found. So how effective would it be for our climate if we were to change what we eat? If a person who eats everything, plants and animals, an omnivore, were to go vegan for 1 year, that would save about 0.8 tons of greenhouse gases. 0.8 tons. You might ask, is that a lot or not? Contrast that to one transatlantic flight from the United States to Europe per passenger, which emits 1.6 tons. So if I fly to the Netherlands or to Germany from California, where I live, then that would generate twice the emissions that I would save if I were to go vegan for 1 year. So I would have to go vegan for 2 years to offset one flight per passenger to Europe. And that's not going to happen, okay? Not going to happen. If the entire United States were to go meatless Monday, and some people propose that, it would reduce greenhouse gases by 0.3%. And if the entire United States were to go vegan, and that's not going to happen, but if, just as a theoretical, that would reduce greenhouse gases in the United States by 2.6%. I can tell you that the notion of changing the diet to save the planet is a no-starter. It will not happen. And it will not reduce greenhouse gases in a way that's strong enough to affect our climate. In addition to this, I took it upon me to talk to the president of an important vegan society of the United States recently. And I want to make very sure that everybody understands I have no problem with people being vegans or eating whatever they want. But I have a problem when they tell me what to eat. But I talked to the president of the Vegan Society of the United States, and I asked him, what is your greatest challenge as a society? And he said to me, the greatest challenge is the so-called retention rate. And I said, what does that mean? And he said, retention rate refers to how many vegetarians and vegans stay vegetarian and vegan for longer than 1 year. And I said, well, how many? And he said 84% of all vegetarians and vegans stop being vegetarians and vegans after 1 year. I said, sir, that would mean that for every one active vegetarian and vegan, there are 5 former vegetarians and vegans? And he said, yes. I'm just showing you that because to me it's very clear this is not the gold standard. This is not the way forward. This is a diet that's pretty extreme and that will not get us to a point of drastically reducing our impact on our climate. If you are really interested what it is within our food system that has the worst impact on the environment, on greenhouse gases, water pollution, air pollution, everything, what is the worst thing of our food system on the environment? It is depicted on the next slide. This slide, ladies and gentlemen, shows the amount of food associated with an American family that is wasted every year. Wasted. 40% of all food produced in the United States, 40% of food produced in all developed and in all developing countries of the world is wasted. It's never making it to a human digestive tract. While in developed countries, this food waste occurs at the consumer level, in our households and restaurants. It occurs at the producer level in developing countries. Their farmers don't have the capacity of harvesting on time, transporting to the markets, and so on. But this is a number that holds globally, and it is just unbelievable to me that we allow this as a human community to happen. And then we think about all the things that we can make people change individually while ignoring such a glaring problem. So, just want to point out 2 documents. One is a pathway to climate neutrality, a document that you'll find on my center's webpage, and a document that I seek to change or adapt to Uruguay. I think it's very important for you to know not just how many greenhouse gases you produce, but how everything can go with respect to achieving climate neutrality. What the steps could be for you to achieve that goal of not adding additional warming to the planet. So I'll work with your teams on using not just GWP 100, but also GWP star to get you to a point of climate neutrality in the years to come. This Rethinking Methane here is a video, a 5-minute video that is on YouTube. You can easily read it and share it. And I want to point out that my center has a blog, and we write many stories and so on in response to media reportings and so forth. So I encourage you to visit that. And this here is my Twitter handle. If you so wish, you can follow me. GHG Guru is my handle. And with that, I thank you very much for your attention, and I'm very happy to entertain any questions you might have. Thank you.